Ole, are you ready to take over from me?
Yeah, I'm ready. I'm
Yeah,
ready.
so
I just there is a question how to make my code faster, which intrigues me. So yeah.
Yeah, thank you. Please introduce yourself, and then I will stop sharing.
Yeah.
Yeah. Yes, Ole.
Yeah, I'm trying to run there. It's a bit slow. We tried this a few minutes ago. There. Shit. Now you should see the NRIS logo, etc.
Yes.
Good, good. Then we're okay. And you can hear me quite nicely.
Yeah, perfect.
Good. Yeah, my name is Ole Saastad. I come from University of Oslo. Been here for quite some time now, working with HPC and different things. And I think we just go straight on it. We will try to cover some ground with best practices, what to do and what I don't really like to talk about too much what we shouldn't do. But I'm trying to give some best practices. And from my definition of the thing is I've tested it and it works. It's not really probably when I write the best practice guide for the EU projects, we don't really spend all the time getting the one single % more performance. We spend on something that actually is simple to learn and actually work and give decent performance. So we go straight on it. I've tested it and it works. And the higher order is how to improve efficiency, performance, experience, resources, good behavior, sharing experience, and help onboarding. And for those of you who want to scan the code, you can see the Unix hierarchy and you can put yourself somewhere on that scale. The first onboarding is for those who are unsecure with the concept of a terminal, who are not really used to the command line, and they take it from there. Know your workload. Know your, Sun Tzu talks about know your enemy and you can fight any battle, but this is the same thing applied here. Understanding what's going on. What is my job actually doing? And the next point in my list here is remember that you are not alone. On your laptop, you're alone. On your Raspberry Pi, you're alone. On your home computer, you're alone. On your desktop, you're alone. But on a HP system, you are not alone. So if you really screw up, you might screw up the whole system for all the users. So especially from when doing I/O, because I/O is a bottleneck and a shared resource. If you screw up on a single node on Saga, you screw up for a lot of users. If you do that on Betsy, you don't. You only screw up for yourself. But remember, you are not alone. And don't waste the resources. I mean, we'll cover that one because it's very easy to do stupid things. And my favorite is from programming in C++. It's a waste of resources unless you are good to program. If you know how to program, C++ is excellent. If you don't know how to program, it could be a nightmare. So think of this next time you run into something like in C++. And there are so many pitfalls you can go into, like array of structures and structures of array, etc. So be careful. But for the moment now, I'm assumed that you are not developers, and I will cover basic things. Then the scenario is that you are faced with an unknown executable and so on. And how do I deal with that? But and some parallel program. You can see from the picture, parallel program is not so easy. The old famous Seymour Cray once was asked about parallel programming. He talked about having 1,000 chickens for the plow instead of one big bull. But progress is now showing that we are forced to have 1 million chickens or 1,000 chickens before the plow, because this big bull doesn't exist. So we are forced to do parallel programming, and we might easily end up in the situation on the drawing. So what kind of information do I actually need to do this thing? How do I get the data? First of all, is your application actually running in parallel? Is it built in parallel? Are all the executables independent? So we'll take a very simple scenario when you have a huge amount of totally independent work. Sounds strange, but for those of you who have heard of Monte Carlo simulation, where you put your hand in a ball, pick a number, perform a computation with that data set, pick another number, and do computation on that data set. They're all independent. And you don't really do any kind of special programming. You can do something called array run, which is array jobs in Slurm. It's a special case for trivial independent jobs. And sometimes we've seen people struggle with MPIs and so on, where you could actually use array jobs instead. So I'll cover that one because it's the first simple step towards parallel programming, which doesn't involve any parallel programming, just a massive amount of different jobs with same program, but different input data. So gathering data about my job is the application. Assume that you didn't write it yourself. If you did, then you will know. So is it a single core, multi-core, shared memory, distributed memory? The difference between shared memory and distributed memory is that if it's shared memory, you have to see all the memory on the system. If it's distributed memory, you can have it on different computers and exchange data as with messages between the computers. And if it's a multi-core, then it's normally shared memory or, yeah. Then gathering more of data about my work, memory footprint, cores, processors, scaling, input, output, and runtime. This will be covered both in my session and later sessions because it's very important. Memory footprint can be inferred by knowing your data structure. So if you write a program yourself, you could actually sit down with pencil and paper and take the data structures and calculate how many bytes and they are using. But if you don't, there is no better way than trial and error. A lot of things with supercomputing and scaling, etc., is based on trial and error. So processors and cores, you scaling, that's something different. You have to figure out how does my program scale, and that's not easy to tell without any experience. There are models you can use, but in most practices, trial and error is actually the best way. Input and output deals with the files. I'll cover where to put the files and how things are actually laid out on a supercomputer. And of course, the runtime. Runtime is not so easy to calculate either, because does it grow linearly with the data set? Does it scale logarithmic? Does it scale with n power of 2 or n power of 4 or etc. and m to the 8 or whatever, or even an exponential thing? So applications. Single node applications is a single or multi-core shared memory. There are some keywords you can look up if you are downloading it from somewhere. It could have the keyword OpenMP. It could have the keyword multi-core, shared memory, threaded, pthread, POSIX thread, or NCPU. On the right-hand side, I give you some command lines that you could actually try to test to look for what kind of applications you have. This LDD is a magic function. It lists out some libraries, etc. And you can grep for either OMP or thread or whatever. Or you could even run the nice program called strings, which is a program that prints out any sensible character strings in bytes that can be looked upon as printable characters, and look for occurrence of OMP or thread or whatever. So this is quite nice and powerful things. It's nice to try them on different, because you never know what kind of strings that are hidden inside the program. If we then go to multiple node applications, which is this called distributed memory, and it's generally MPI. There's other paradigms for running in parallel exist, but MPI is absolutely the most common. I never think you will ever see something else than that. an MPI. It might be for those who run Gaussian that are exposed to some this Linda system and so on, but mostly it's MPI. And you can grep for MPI, and you can grep use string and grep for MPI. Then you will know whether or not your program is shared memory, with other words, a single node application, or if it's a distributed one that can run on a set of nodes. So now we know that we have an application of some type, and how do we run it? We have memory and cores and runtime. What do I set or request? So it's doing manual work. I can just do it by think that I do the memory footprint and so on. I calculate manually. It's not so easy. I can ask other users, because some programs have been used by the colleagues in the hall, or you can find some on the internet or so on. Other users have success with these settings. You can guess. It's also a nice one. And the best trial and error, even when it fails catastrophically, you at least know that this doesn't work. And sometimes it works and you're lucky. Sometimes it just crashes and you're unlucky, but you learn something. So learning along the way is normally the best one. And of course, run Slurm with test jobs and explore parameter space. But as you will understand, that memory footprint, wall time, number of cores, etc., there you can have a quite high dimensional space. So if you want to explore the whole thing, it will take more or less forever. So you need to combine trial and error with guess, or the above. But I can tell you there is no magic bullet for finding out this. In memory footprint, you might be lucky to see if the data structures are fixed and if you know the source code. But the scaling is a bit harder. Even if you have written the program yourself, predicting scaling is quite hard. So back to the one I said about where we can think of the type Monte Carlo experiment, or an experiment where we don't really have implied parallelism in the program. We have a single executable. It could, in principle, use many cores, but I've said one here is a single core thing, which actually are independent of anything else. But you have a set of test parameters you want to explore, typical Monte Carlo simulations. So you make a list of input, and you specify to the Slurm that you want to run a set of those, and you use the number to pick your input data and just launch a bunch of them. So you can launch a huge amount of them. So in my case here, I just took one. I could take more and so on. And I also did a very simple one. I did just copy some data from the random device and so on, and print it out to a file. I think if you set n tasks to more than one, of course, it would be more sense. Put it to 10 or 2 or 4 or something. It should make a nice one. And you will have in my case, on the right-hand side, I specify array from 0 to 1, 0 to 3. That will give you four instances of that one. So that will provide you with, I see I have on the dd command line, the last command, there is an output file, of equals output file, random rdn dot slurm task array, task ID. That will be 0, 1, 2, or 3. So you can see the output files. And of course, they will not contain random numbers in my case, but you could put in a large Monte Carlo simulation for each one of these. So this is a special case where you can actually run things in parallel, where you can take advantage of a supercomputer without any parallel programming. So it's a simple thing. Another thing that you could do to learn some about your program is to run interactively. So for very short jobs, less than 5 minutes and with not an unlimited amount of memory, because this is the case where you are sharing with others. But if you have a reasonable amount of memory and a short runtime, you can run it run it interactively and just check input and so on. And when you're satisfied, you could scale up the input to a reasonable size and the wall time to a reasonable size. If you want to do more, you can just request a node using Slurm and run interactively there. And you can even specify the whole node by asking for all the cores. And you could actually see what the memory limit, how much the memory limit are. And if you run over the memory limit, you will be killed anyway. So it's not really the end of the world if you screw up. So that's why if you request a node by Slurm, you have to read the manual or documentation for about interactive jobs. This one will be covered at length, but I'm just teasing you that there are 2 programs that can help you with providing memory and footprint in cores. Cores you already know because you have to set it yourself, but the amount of memory could be found by using this. And I know Radovan will cover this in length and how to do it and etc. But remember that those 2 programs are really your best tools and simple tool to do it. Maybe top is even simpler. I have put a page top here. It's very simple. They are quite simple. So now for a bit of hard theory. We are faced with CPUs and cores or whatever. There are also things with hyperthreading, symmetrical multiprocessing, and a lot of these strange words that comes up. There are also things like physical cores. The drawing you see here is a modern core. Some genius people discovered that since this core has a lot of executing units, executional units inside, and since you often have to wait for something, it could be beneficial to have a really infinitely fast context switching, or actually run 2 or more streams of instruction in parallel through the core. So you put in more registers, 2 in for the Intel and AMD processor, the x86. They have 2 sets of registers, and they can actually launch 2 sets of execution, 2 sets of instruction streams simultaneously if you have the hyperthreading on. The practical offspring of this is that seen from the operating system level and seen for you, it looks like you have 2 CPUs or 2 cores. For all practical purposes, the operating system think that you have 2 cores for each one of these. So you have twice as many cores as you might consider you have. It's not so easy because you have 2 times the amount of registers. You have 2 times the amount of some of the things, but some of the things aren't shared. So it's not easy. So I usually refer to these cores as virtual cores, because you never know what you have in there. But you know that you can run 2 instruction streams at the same time. And now comes the important thing for high performance computing, is that if you run 2 streams and they are competing for the same resources, you are sharing the resources. And since there is an overhead and a lot of administration work to deal with this, you might be better off turning the hyperthreading off on HPC systems. On other systems for web servers, laptops, etc., it's much smarter to have it on, because you are not running identical instruction streams. So on the picture, I've taken an ideal system where I have two instruction streams entering the four-way cache at the top. Cache can take two instruction streams easily because it's just a memory. So that's piece of cake. They run to a decoding unit that can easily accommodate two instruction streams. They can do 4 and so on, but in the AMD and Intel case, they can do 2. Then they can run, you can see they can do 4 instructions per cycle. They can move this into micro op queue, which can easily take 2 instruction streams. They can take even more because the instructions are broken up to micro instructions. Then they are dispatched into the executional units. There is one executional unit for dealing with integers, and there is one executional unit dealing with floating point. So they do some renaming just to have more space for registers, etc. They're put in a scheduler, they're put into register file, and finally they are going into the arithmetic logical unit where you add the 2 numbers together. 1 plus 1, 2. Then it's put into a cache, data cache for output, easy. Simultaneously, as I go through this detailed talk about the integer, the other stream enter the micro queue and enter the floating point unit. The same thing, and it gets scheduled to the multiplier unit. So pi is multiplied by 2, and the answer is copied to the cache. Those two things happen at the same time simultaneously in parallel. So the performance looks to be twice as high. And in this case, it actually is true. You get twice the performance in this case. Most of the time you don't, because if we were running a normal MPI program, the parallel program will launch n amount of n executables simultaneously. They are all identical because MPI programs are, all the MPI ranks get scheduled 1 rank per core. Those 2 ranks are identical executable programs. So you will enter 2 instruction stream in the blue path. And since it is different executional unit, there are 2 multiplier units, you might have some speed up, but in most cases you don't. So the good practice is to turn it off. On some system, we have actually done that. So, and with good results. There are tests that can show, I'm also run tests that can show it's better to turning it off. But for general purpose use, turn it on. So I hope I covered some of the hard stuff about virtual core, physical cores, and so on, and threads. A thread can be thought of as a stream of instructions. Your nicely written C or Fortran or Python programs are broken up into instruction streams and scheduled on the processor. So hard theory work finished. So how do we actually run parallel programs in the right way? Here is the SPatch commands put up. I put up 2 nodes. N task per node is 4. And there are 1 CPU per task. So this will be a typical MPI program. And the runtime and the memory per CPU is 2 GB. But you see, this is a 5-dimensional space. I say only educated guesses are possible. So here we have to combine trial and error with educated guess. If this is an unknown program and you don't really know how it behaves, you just have to guess. And the exercise today is about scaling, so we're helping you to run it better and actually see the scaling yourself. So the best practice is to start slow, start with a few nodes, few ranks. There are a number of ranks. MPI ranks is number of nodes times the number per node. So we have in this case 8. and there is one CPU per task, so there is only one CPU per MPI rank. It's possible to do hybrid programs where you have combined several threads per MPI rank, but this is this is next level. Setting times high, you could in principle set it to a week to be short, but then your queuing time might be very long. So good practice is to try to set it slightly longer than your runtime. But if you don't really know what your runtime is, then you have to do some trial and error and run it and see how long it takes. And then next time you ask for slightly more time, 5%, 10% or something like that, or just a little bit more, because sometimes the program runs slightly slower than you might expect, and it's very not bad if your program would get killed 2 minutes before finish when it took 2 days to run. So some slightly longer, and you only get accounted for the actual runtime. You don't get accounted for the wall time you put up here. So this is important. It doesn't really matter much if there is a little queue to have the runtime specified the wall time longer, but you might be faced with a longer waiting time in the queue. And when the test job finish, you get a lot of nice, valuable feedback from Slurm. So do keep the run files, and I can say it now, and I will say it later. On the troubleshooting, that please do review several times and look for all the clues in the Slurm log files. Here we can actually see that maximum resident memory is covered. We can see how long it took. We can look at average CPU and the exit code and so on. You will be taught later on the importance of the maximum resident and so on. But there is also about data, about tasks and pages and so on. And in this case, it's 0, so it didn't matter. So, but I'll have another example with some more data. But the input files are important. The output files from Slurm are important. So before you submit a ticket, you should really review the log files and looking for clues. If we change to the all important things about storage. Storage is important, and with the fact that we are dealing with the parallel file system, storage is even more important, because a parallel file system is a shared bottleneck for all of us, and it's residing on spinning disks. While it can do things in parallel, you can buy bandwidth by having more disk, but latency you cannot borrow. It takes a certain amount of time to make a good wine, but if you have enough breweries or winemaking vineyards, you can have as much bottles as you like, but it takes a considerable number of years to make a good one the first time. Same applies here. You can buy bandwidth, but you can't buy latency. While for storage, this is not really the true anymore, because you could have solid state storage, and I'll have covered this later on, that there are tricks you can play. And this is from the local cluster. Here I are asking for very, very large file that are twice the amount of installed memory to bypass any caches and so on, to get the real performance of the storage system. As you can see, random read is a nightmare. In any case, even in the best possible case with memory chip storage, random read is bad. But for spinning disk, it's really bad. I used to say when I'm teaching that, consider this disk as a metal disk where you have glued the tape on. Conceptually, there is actually no difference between a disk and a reel of tape. So except that the tape are put into a disk, and you can actually jump faster between the sectors on the tape. So, but if you think of a tape, you have to do random reads. Then you have to start somewhere on the tape. You have to seek for the right sector, read that sector. Then you have to spool the tape back or forth to the next sector, read that one, spool the tape again, and you can easily imagine that this takes forever to do. So that's why the random read is so bad. Random write is slightly better because when you write to the disk, you can actually cache them and have a queue. You can have quite a long queue of random writes because all the random writes and all the random read are independent of each other. So it's fire and forget. A random write is a fire and forget. So you can stack it away because you might expect that sooner or later you will write to places that are co-located in space on the tape. So you can actually do random write that's slightly better. But random read, you never know what the future will give you because this is random read. So when you have placed yourself on the tape, you never know whether you're going backwards or forwards or where you go. So that's why random read is so bad. So if you can avoid random read, you're in a good position. So yeah, random read is bad in any respect. But if we are not in that regime that I overrun the memory totally, Linux is so clever that it tried to cache disk access. Yeah, a nice example from the past when the disk was noisy is that you run make and the disk goes like a popcorn machine. You do a little change and run make again. Then it's silent because all the files have been cached in memory. And if you are dealing with a file that are very small compared to the installed memory, then you are in a good situation because then it cached in memory and you can see random read and random write are quite good. So you are in a lucky position. So for most of the time, if you're dealing with smaller files, you are happy. And you can see from this one how you are accessing the files does matters, but normal disk access is normally cached, so you can just consider the blue line. Parallel file system operations. If you copy files or dealing with files, doing it in parallel always helps. This is the performance of the local system in Oslo. You can see going from 1 to 32, it increased quite dramatically. Well, not that dramatically, but it increased performance quite good. So if you can split it up to do run things in parallel, like copying files, if you could take 10 or 16 copies in parallel, it will be much faster than a single one. This is a best practice sheet, and I don't really want to read through all of this because we don't have time, but copy this down and review when you have time and actually look for what you can do. The only thing is important here is that local scratch doesn't exist on Betsy, and on Fram it's small, but the local scratch is actually memory based. It's either SSD or NVMe RAM, so it's actually much faster. So you could do some tests, but if you have a random access file, local scratch is your friend. And try not to copy files because all the thing that starts with cluster, they're all on the same storage. /cluster is the storage, and moving files around on that file system isn't really helping anyone. So don't copy files from one place on cluster to another if it's not files that you're going to write to. Then you can't overwrite other people's file in the project directly and so on. But if you are reading files, don't bother to copy it because it's on the same file system. If you do random read, you should put it on local scratch if it's possible with size and so on. You can see all clusters are on the same one. And the local scratch are really good, but Betsy has only the cluster. It doesn't have local scratch. Now we are drawing closer to the actual exercise.
Ole, may I ask you something?
Yeah.
Thanks. Could you define what do you mean by random read? Thanks.
Random read.
Yes.
Yeah, I'll put this one up again so we can. Random read is you open a file and you draw a random number. You spool the tape by using a command called seek that asks for sector or byte number this and this, or sector number this and this. So you've probably seen all the movies when the tape is spinning like crazy, and then it has a counter that can count number of revolutions, so it can actually place the reading head quite near to that sector. Then read a byte or a character there and print it on screen or on a file. Then you draw another number with a different sector. Then you have to spool the tape backwards and forwards to reach that sector. Read the character, store it to a file, and draw another number. So you are actually accessing random sectors on the tape without knowing anything. It's the worst thing you can do, but it's a very nice test of showing how bad random read is. And some programs actually do this. And it's a nightmare. Does it help?
Yeah, thanks. There was a question on HackMD, so I just.
Oh yeah. No, I hope I covered it. Otherwise, we'll have to take it more in depth in the question and answers. No, scaling is probably the most cause of misuse of a computer system. This is a very, very old figure I made many years ago, where 1,000 cores was quite a lot. Today is nothing. I mean, it's the smallest job you can run on Betsy. It's about 1,000 cores. Perfect scaling is easy if you have independent job. As I said about these array jobs, they are actually independent and they will scale like the blue line. Few applications do that. Some applications I've seen scale between the yellow line and the blue one, but in a straight line, which is really good. But the only thing that, because I think they are, is that I'm actually in the right part of the diagram, but the numbers are different. Sooner or later, you will end up in the blue or green one. So when you run the scaling, sooner or later, you will hit either the blue or the red one. If in any case, you are misusing the resources if you are on the right-hand side with the blue and the green one. If you are on the red line, the red or the green, if you are on the red line, you see that it doesn't matter how many you use here. You can use 10,000 cores, performance stays the same, which is bad for the others, but it's okay for you. If you are on the green one, it's bad for the others and it's bad for you, because the program actually slows down when you increase the number of cores. So the exercise that we can do is to actually run the program and do that. And yeah, I run you through some scaling theory first, but we can do this. And if you are like these unlucky ants here, this is bad. This is the first one, is a very sinister law. It's a gloomy law called Amdahl's law, which predict that it doesn't scale at all. This is a bit tricky one, so you have to read this when you have time. I don't have time to go through it here. So this law from 1967 predict that you couldn't really do parallel programming at all. Gustafson's law, on the other hand, predict that it's very nice, because if you have enough work to do, you can actually have a very nice speed up. If you set S to 0, you get speed up of n. So if you have enough work to do, you can actually achieve a very good speed up. This is a typical thing of what we can see today on the scaling. This is another one that we'll not cover. And if can you see my window here?
Yes.
It's
Yeah.
fine.
Yeah, but the other thing is, how do I increase the font size? It didn't like that one. Large. No, okay. Can you see the point is that you should copy this file. There is a place for them that it's on the HackMD or
Yeah.
where you can copy it.
Yes. I will.
And there is a very simple thing here to run. Everything you could just do spatch and sp.run, and that will run it with 4 tasks which I put in here. Then you could put in 4, 9, 16, 25, 36, 49, etc. And 49 more than 49 doesn't give you anything. It's a square numbers. And run it with different one and note the scaling. There are 2 things you can consider. You can either consider the total number, the total performance, or you can consider the performance per processor. So make your choice and run it with 4, 9, and it should be fairly simple. Before I did ask the people to when we have a classroom to distribute by themselves so that they could only run one each and then share the numbers, but it's very fast to run. And then there is a break until 10. I think if you start playing with it, then we can reconvene at 10 and see if we have some interesting numbers to look on scaling. Up. This one is a one I took the same benchmark, but for the MG. It's not good if you spend 32 processors doing nothing, as in the red curve here, because other users might benefit strongly from those, and normally there is a long queue on these systems. So the running 64 in this case on the screen is typical bad practice. Good practice is to run with 18, 16, or maybe up to 32. But you see what you get extra from doubling the number of cores from 16 to 32 is very small. You see, you get much more benefit from going from 4 to 8, and also from 8 to 16. Going to 32 gives you better performance. Yes, it does. Absolutely true. You get shorter runtime, but you spend a lot of time waiting by running it. So your performance per core will be much lower. So there is a trade-off here. You want to have the result as much soon as possible, to have the much science done per day as possible, but you're also wasting resources when doing so. So it's a trade-off. And try to be nice, even though you might get more science done by yourself. This is typically referred to as tragic of the commons. I mean, it's good for me, but it's worse for the others. So try to find a decent trade-off here. But we could spend the time on the rest of the day by talking about this, but I have something to cover by troubleshooting. The most important thing when things go really, really wrong, if you have time, you could look the film that I pointed to. Keep calm and carry on, because when all the alarm bell sounds, the most important button is to silence the alarm bells so you can think and keep calm. And what do I do now when things go really wrong? But in order to go really wrong, we can start here. This is a nice one. Can you blame somebody else? Yes, you have no problem. So where do I start? When do I start? Does the test if the application actually launch? This you can do interactively. You can, first of all, you can check if it has all the libraries available. It might not. You run an LDD, which is the fancy command again. This will print out all the libraries. And if you see something not found, you have probably a missing module or something else is missing. These are libraries that need to be resolved, otherwise your application won't launch. So here it's by all chances a missing module. There might be modules that we don't have, we should have. So this is another thing. If you get not found and you cannot really figure out what kind of module it is, then it might be time to file a ticket. How do we find the missing module? We already know about the find command. This is very hard for the file system, so don't run this command too often, because it's running through the whole structure of this is time consuming and hard for the file system. But this is, if you can't find the module you need, this is the way to do it. Look for the file that you actually saw was missing and issue the command. You'll see that it comes up with cluster software, Intel compiler 21.4, compiler 21. Then look for something that match that one. Use the spider, module spider Intel compilers. You see there are two ones. There are two modules that contain this file. So you can pick one of those, and that should resolve one of the ones that the one I had with the lib port for .5 so shared object.5. So we don't have time to go in really depth into this. So, but we continue with, we have an MPI problem. We discovered that it doesn't resolve the MPI. And of course, if we have lib MPI SO.40, we could expect it to be an open MPI. It could be an Intel also, but then it will probably say IMPI. So we try first, we guess that the lib MPI is I know it's open MPI, so we guess that first. If it said lib IMPI, it will be Intel. So we go for the open MPI. We get an answer. We find the versions and try some of these modules and run LDD again and see if it resolves everything. If everything is resolved, we're good to go. So that's only the beginning of our potential problems. There is no end to what can happen. So normally I try to stay happy, and I say that if it works, no, a computer system is so complicated that it shouldn't really work. So when it doesn't, I'm right. And if it works, I'm also happy, because then it works. So in both cases, I'm happy. So, but you get this, this one is a rather tricky one. Illegal instruction. This comes from times where you probably have built the executable, or somebody else have built the executable for the Intel compiler, with the Intel compiler asking for Intel specific instructions. There are special instructions inside the executable that test for the processors you have you're running on. And since Betsy, for instance, have AMD processors, this one might kick in. There are ways of circumventing this and get around this by fooling the executable to think that it's running on Intel. It's a very simple function I wrote that just report yes if it asks for Intel compiler. But this is covered in the documentation. So if you find this one, note that it's probably built for Intel, and there are probably some ways around it. Then, does your Slurm job start? Does it accept your input? Then, in many cases, we are not even capable of starting the job. So SPatch complain that there is a list of things that can go wrong here. I'll cover most of this in detail further on. So the association job limit, resource limit, time limit, quality of service, and resource limit and time limit. So there are different things that can go wrong. So we have invalid account, partition, combination specified. This is the project name, etc. So you need to figure out what the project names and so on. If you try to run in a wrong queue and so on, let's say if you, here we have been allocated with the one called 99, 90, 89. I always run in 99, 99. So if I try to use this for this training next time by the same, I will get this error. Then there is also a problem that user size and time limits and so on. If you ask for too small jobs or too large job or too many tasks or whatever, then you also get that it violates accounting. Also, if you are doing things asking for too much time, etc. Which comes to the next one. Requested time limit is in that. If you put in a year of the time, a year, 365 days, it will not run because there are limits to what you can run normally a week. But sometimes if you are close to a maintenance schedule, that time will be shorter. So Slurm tries to emit sensible error message and read those carefully and see if you can actually resolve the problem yourself before submitting a ticket. Point is saying this, that we can handle such ticket, but you might not get an answer before the next day. And then you could be much better off by spending 20 minutes by figuring it out yourself instead of waiting one day. So that's why reading the error messages that Slurm output is generally good. And if you also use Google to ask to search, you might get some good answers. And then you solve the problem yourself, and you don't have to waste time by waiting for an answer on your ticket. This is a very common one. Association limit, billing minutes. This is mean that you are not actually out of time, out of quota. But Slurm think that you will be if it would allow this job to run. So point is that the wall time count on your core hours when you submit. When your job is actually run, you only get accounted for the time you actually run. So if you specify 24 hours in your time limit, Slurm, when it tries to launch, expect that it will run for 24 hours. But you only run for 1 hour. So you have quota left for 1 hour or 2 hours, but not for 24. But Slurm won't allow you to start because of it thinks that you will overrun your quota. So this is a common ticket. You can run the cost command. I put in an interesting one here. I have 81 and task 81 and a week time running. That will give you quite a long time. The last line show you a nice trick that you can play with not on the, well, you can put it on clusters, but you need to launch the right module first. But if you have replaced the desktop calculator with Julia, as I have, you can just echo this in, and you see it get 13,000, which is clearly more than 1,000 that you have on the Optimist queue. So I got this error, and you can use the quota and see, and the cost command and see how much quota you got left, and see if the time and the number of tasks multiplied together are smaller or lesser. Then there is submission failure, invalid account, partition combination. This is generally the wrong project name. Misspell project, partition, or other selection resources. Check spelling in the Slurm account. Maybe you are trying to run in a project that no longer exists, or you misspelled, or other strange things. Like you would also, if you try to run using the reservation that we have for this training tomorrow or next week, you might get problems with that too. So, and it's easy to reuse the script for new jobs, and it can easily propagate lines into a new script from the old one that you didn't think of, and then suddenly you want to run and it doesn't start. So review the script every time you start a new thing, a new project, or the best thing was actually to start writing the Slurm script from scratch each time. But most people just copy them from either get them from someone or copy them from their older ones. So and then all lines could easily get propagated into a new one. So and when that happens, you get the error message like this. And then the quality of service, it could be, I try to run, I managed to do this during the exercise. I put in 81 because 9 times 9 is 81 and for the script, and I couldn't because I violated quality of service. So there is a limit on number of nodes, number of cores maybe outside the limit, too few or too many. Too few, it doesn't apply to Saga, but on Betsy, you're not allowed to run small jobs. Wrong quality of service, there is some different quality of service you can have. You can have interactive or development and so on. Or maybe the wall setting is too long and so on for that queue, or too short for that queue. So again, Slurm, try to emit sensible error message, so read carefully. Requested time. Time limit is set to long. Normally it's 1 week. But it also might happen that there is a downtime there is a downtime schedule, a maintenance is scheduled in the future. But that future might only be 48 hours away. If you try to run something with a week time, then you won't be able to do it. And you might get this one. This one I didn't actually test because I couldn't. So, but you cannot submit jobs that have runtime into the maintenance. So you will not be able to do it. So if you are getting strange errors that this used to run yesterday, but not today, you might get hit by that one. And of course, there should be something in the log that maintenance is scheduled. Again, your errors should be sensible, but it will not say that you are running into the maintenance. That one you have to figure yourself. So your job got submitted, but failed to start. What could that be? It hasn't started yet. It's only in the queue. It could be one of these: priority, resources, dependency, or reservation. Ask Slurm. You can ask Slurm a lot of things. And note the job ID. This is the one that we run today. And it's in the priority. So what's happened? I have the job ID. This is the important number. And you could ask Slurm for a lot of details. You could use S control. It's not with the capital S, it's with the small s, but the presentation program make it, since it's the first character in the sentence, it's make it capital, but it's a small s. S control, show job, and the job ID. And warning, you get the page full of data. We have to turn this data into some kind of information. So what do we need? We know that job state now is running, so it's actually running. It's a good thing. But if not, it will print out things that you actually need to know. when will it start to run, which is most important in there, that will be printed, or submit time, eligible time, start time, end time, deadline, preemptive time. There's a lot of things that you could get from this. You just have to not to be intimidated by all the numbers. Take it line by line and see, does this apply to me? No. Take the next line. Does this apply? Maybe it does, maybe not. You see the time limit is 5 minutes and so on. Going further down, you will see that I'm not running in the normal partition. And going further down, you can see there is a list of nodes. I'm running on C232 and C237 and C545, C546, and C560. So I've spread out over a number of nodes. It will also print out how many number of nodes I use. 5, 49 CPUs, 49 tasks. There are 1 CPU per task. It's also said something about the memory, because I asked for such and such memory. That will give me 49 CPUs, 196 gigabytes of memory in total, spread over the 5 nodes. And then a few other things like minimum memory is 4 and so on. And the output files and the working ID, standard error, standard in, and standard out. So this is important command to write down, and it's S-control show job and your job ID. So it's a lot of data, but don't be intimidated. Break it up line by line and you will divide and conquer. So back to the simple list. Priority. That means that there are jobs with higher priority that are waiting for compute nodes. So you are not priority boarding, you are running with some kind of priority. This priority increase with waiting time in the queue. So the longer you waited, the higher your priority becomes. So sooner or later, your job should start. But your priority is set by the number of nodes, number of cores, and your scheduled wall time. So if you schedule wall time too long, you will get longer wait time. If you schedule wall time to 1 minute, it will start sooner. But of course, then you will run out of wall time very rapidly. So I got a comment from here, which is you can cheat. I mean, if you have the root privileges, you can go in and set it longer while it's running. But that's only is for the staff to use, and with great powers comes great responsibility. So we don't do that too often. But of course, if you have set it to 2 days and suddenly you discovered, wow, I should have set wall time to 3 days, then if you have enough time, you can submit a ticket. And from time to time, we get such tickets. But of course, setting it outside of a week is generally not done, because that's will violate the rules for running. It is technically possible to do so. If you have extremely good reasons, you might try to persuade the people on the help desk to do that, but most time they will say no. But increasing from 1 day to 2 days is a piece of cake. The other thing that could stop you from starting is resources. Job is waiting for compute nodes to become available, which is the most common one, because there is a limited number of compute resources. So you just have to wait, be patient. And then again, when there is such a queue, then only using a sensible number of cores, as we discussed before under scaling, is important to minimize the queue. Dependency. You might have set up some dependency so that this job won't run before the other one is finished. Some people like that so that they can have a long pipeline of jobs that waiting for each other. Then there is a reservation. The job is waiting for its advanced reservation to become available. That's possible. and you have the job limit. Maybe you have submitted so much jobs that you are not allowed to submit anymore, or the job association has some resource limit, association limit, resource limit. And there are a lot of details to all of this, but you can either go on the web and search for SPatch manual page, or you can use man SPatch, because there's a lot of details hidden behind all of these keywords. And it's too much to cover in a training session. This is some of the things that I can only provide you help to where to look for, and man SPatch is a very good thing, or on the internet. But you SkedMD has all the man pages on web, so they are easier to read on web than to read just on text on a small window. So, does your job fail? Now we actually managed to start a job, but it failed. So Slurm, again, does it best to emit sensible error messages. Read the out file or error files carefully. And it cannot be stated enough that you have to scrutinize those files before submitting a ticket. And when you submit a ticket, then copy the relevant thing. Just do not just attach the log files. That might be okay, but if you read the files carefully, you will easily spot where the actual problem is, and that will make it easier for the first line support to see it in the text, what the problem actually is, instead of having to download the Slurm files. So there are very few errors escaping login to the Slurm file. I'll give you one later on, that when you get nothing. But that's another fault that Slurm cannot possibly deal with. So read the Slurm files when things go haywire, and try to think why it goes haywire. And if you are really stuck, take a coffee, think, review, and if you're still stuck, file a ticket. So this is a common one. It's cancelled because of run out of time. You specified too short time. Be aware that a job can vary highly in runtime. It should, in principle, take the same amount of time for every run, because this is a deterministic machine. But the I/O system might be very slow or sluggish, or from time to time actually hang because of misuse, by intentionally or by most of the time is unintentional misuse, because people do things they shouldn't do, or they do too many things they shouldn't do. So the file system could cause the program to take much longer time.
Ole?
Then, yeah.
Can you finish it in 3 minutes? I see like
yeah, I can do that.
Yeah,
I can do that. I thought it was until 10.
14.
10, yeah, sorry. Yeah,
that's fine.
Yep.
Thanks.
This is the real bad one. This is the auto memory handler. You run over the memory limit. But of course, you have C groups that will help you with that one. And yeah. This is the catch-22 situation I was told you about. I run this to play around. I filled up the disk in a batch job. Then there is no way for Slurm to append or write to the log file because the quota is there. So you get no error logged, nothing. The only thing that it's this, you have overwritten your quota. And how is this possible? Yeah, because the quota is checked only every 10 minutes. So I run this job and I overrun my quota tremendously. I mean, I managed to write 80 gig with a quota of 20 gig. And then when Slurm was killed because of overrunning the quota, it couldn't log. So in this respect, there is no log whatsoever. But you'll soon enough figure out that you'll fill up a quota. So that was it.